Assalamualaikum and hi. My name is Muhammad Luqman Aliff. Today, my group and I will be presenting our group assignment, technical report for chapter 7, which is conditional extremum. Before we start, let me introduce our team. ANGELUSWIN Muhammad AIMAN, Muhammad Luqman, Muhammad SAIFUL, and lastly, BATRISYIA. Let's start with an introduction to what we are covering today. The calculus operation is about finding function, not just numbers that extremize, meaning maximize or minimize a function subject to given boundary condition. Conditional extremum problems build on this by adding extra constraint on top of those boundary conditions. The function isn't free to be anything anymore. It has to satisfy something extra. And the key tool that makes this possible is Lagrange multiplier or lambda. It transforms each constraint problem back into the standard unconstrained variational problem that we already know how to solve. This chapter covers 3 types of those constraint problems. First, the isoperimetric problem, which optimizes the functional subject to a fixed integral constraint. Think of the classic example of maximizing area of fixed parameter. Second, the Lagrangian problem, which handle algebraic constraint imposed pointwise on the function. And third, geodesic, which find the shortest path between 2 points lying on the given surface. Each of these follow the same underlying idea. Use lambda to turn a constraint problem into one we can solve directly.
Hi, I am BATRISYIA. I will be covering the isoperimetric problem. In the elementary calculus of variations, we only had boundary conditions to satisfy. The isoperimetric problem adds a twist. We optimize one functional while forcing a second functional to stay fixed. In this problem, we are looking for a function y of x satisfying boundary conditions, y of x0 equals y0 and y of x1 equals y1. But now, there are two functionals, j of y, the integral of f, which we want to extremize, and k of y, the integral of g, which must stay fixed at a constant L. Both are built the same way, integrals of x, y, and y prime, which is what let's handle them together. Moving on to Euler's theorem for the isoperimetric problem. This is the core idea. If y of x extremizes j subject to k of y equals L and is not already an extremal of k alone, then there exists a constant lambda, the Lagrange multiplier, such that y of x extremizes L of y equals the integral of f plus lambda g dx. This turns a constraint problem into an unconstrained one. Lambda is not chosen in advance. It is solved for alongside the constant of integration. We define the auxiliary integrand h equals f plus lambda g, which now plays the role f used to play on its own. This is the 3-step solution to solve the isoperimetric problem. Step 1. Form h equals f plus lambda g, treating lambda as a constant for now. Step 2. Apply Euler's equation to h sub y minus t by dx of h sub y prime equals 0, and solve. This gives y of x in terms of c1, c2, and lambda, depending on two integration constant and lambda. Step 3. Solve the two boundary conditions and the isoperimetric condition k of y equals L simultaneously. 3 equations, 3 unknowns. C1, C2, and lambda must be found together, not one before the other. The reciprocity law says swapping the roles of j and k, extremizing k subject to j fixed instead, give the same extremal curve. Since swapping f and j only risks lambda, it is a handy way to check your work. The generalization extends the method to n function and m constraint at once. H equals f plus lambda 1 g1 plus lambda 2 g2 and so on up to lambda n gm. Solve with 1 Euler equation per function plus all boundary and isoperimetric conditions together. So, extremize one functional while holding another fixed, using lambda to fold both into one auxiliary functional, solve in 3 steps and checkable by reciprocity. Next, AIMAN will be covering the example and the application of the isoperimetric problem.
For my part, I worked through an isoperimetric problem, one of the constraint variational problem from chapter 7. The goal is to minimize j, the integral of y prime square from 0 to 1, with fixed endpoint y0 equal 1 and y1 equal 6. But there is an extra condition. The integral of y itself from 0 to 1 has to equal exactly 3. Because of that constraint, we cannot apply Euler equation directly the way we normally would. Instead, we introduce a Lagrange multiplier lambda and view an auxiliary function h equal to f plus lambda g. Here, y prime square plus lambda y. Applying Euler equation to h gives us lambda minus 2y double prime equals 0, which simplify to y double prime equals lambda over 2. Integrating that twice gives the general solution y of x equal lambda over 4 x squared plus c1x plus c2. With three unknowns left to find c1, c2 and lambda. To pin down c1, c2 and lambda, we use all three conditions together. They cannot be solved one at a time. Plugging x equals 0 into our general solution gives c2 equals 1 right away. Plugging in y1 equals 6 gives one equation linking lambda and c1. And integrating y over 0 to 1 for the isoperimetric condition give a second equation linking them. Solving both together, we get lambda equals 12, c1 equals 2, and c2 equals 1. So our final experiment is y equal 3x squared plus 2x plus 1. And the functional value there is j equals 28. We also check that the second derivative of h with respect to y prime is positive, which confirms this is a genuine minimum, not just a stationary point. One more thing worth noting, without the constraint, the straight line y equals 5x plus 1 would minimize j on its own. But that line needs 3.5 units of area under it, not 3. So the constraint is what bend that line down into our parabola. To wrap up, the same math show up in a real design problem, which is beam design. Picture a taper beam bracket fixed to a wall at one end needing thickness 1 and carrying a load at the other end needing thickness 6. You want the taper to change as smoothly as possible. Since sudden change in thickness creates stress concentration, so that exactly our J functional. And the total material we are allowed to use become our constraint fixed at 3 units. So that's our K. Since the math is identical to what we already solved, the optimal profile is the same curve y equals 3x squared plus 2x plus 1. And lambda here tell us how much that minimum cost would shift if our material budget change slightly. A straight taper would need 3.5 units over budget. So our solution instead remove about 40% of material from the low stress middle while keeping full thickness at both ends, just like real taper beams.
Now that the isoperimetric problem has been covered, this next part will move into the second major category of conditional extremum problems, which is the Lagrangian problem. So, the isoperimetric constraint discussed earlier applies as a single integral condition over the entire interval. The Lagrangian problem works differently, which its constraint is algebraic and it must hold at every point x along the curve, not just as one overall integral value. Formally, the goal is to extremize a functional that depends on several unknown functions, which is y1 up to yn together with their derivatives, which is jy1 to yn equal to integrate from x0 to x1 of fxy1 to yn, y1 prime to yn prime dx, subject to one or more algebraic constraints of the form vi xy1 to yn equal to 0 for I equal to 1 to k. Because these constraints tie the functions together at every value of x, the ordinary Euler-Lagrange equation cannot be applied to f directly. Therefore, a modified approach is needed, and that is what the next slide will introduce. To handle this type of constraint, a multiplier function lambda of x is introduced for each constraint, which is phi sub I. This point is worth emphasizing since lambda here is a function of x, not a constant. This is different from the isoperimetric case since the constraint must be satisfied pointwise along the entire curve rather than as a single integrated total. The augmented integrand, which is capital Phi, is then built by adding f to the sum of these multiplier terms, which is capital Phi equal to f plus summation lambda I x phi I, and the corresponding augmented functional becomes j star equal to integrate from x0 to x1 of f plus summation from I minus 1 to m lambda I phi I dx equal to integrate from x0 to x1 of capital Phi dx. The theorem states that the functions y1 through yn together with the multipliers lambda 1 through lambda m must satisfy the Euler-Lagrange equation applied to capital Phi, with each yj treated as if it were independent. Capital Phi subscript y minus d over dx capital Phi subscript y prime is equal to 0 for j equal to 1 until n. Therefore, these equations solved together with the original constraint equations, which is phi I equal to 0, form a complete system for finding the unknown functions and the multipliers. To see this method applied concretely, consider the following problem, which is find the shortest distance between the points A, 1, negative 1, 0, and B, 2, 1, negative 1, given that the path connecting them must lie on the surface phi xyz equal to 15x minus 7y plus z minus 22 equal to 0. Both points can be checked directly against this equation, and both satisfy it, confirming that A and B do lie on the surface. The arc length functional between the 2 points, parameterized by x, is set up as jyz equal to integrate from 1 to 2 of set 1 plus y prime square plus z prime square dx, with f equal to set 1 plus y prime square plus z prime square. The augmented integrand capital Phi is then formed by combining f with the multiplier term, which is capital Phi equal to set 1 plus y prime square plus z prime square plus lambda x 15x minus 7y plus z minus 22. The partial derivatives of phi with respect to y and z are needed next. Since phi contains no y prime or z prime terms, its derivatives with respect to the prime variables vanish, which becomes phi y equal to negative 7, phi y prime equal to 0, phi z equal to 1, and phi z prime equal to 0. Next, by substituting the phi value that we get before into the capital Phi, it will give capital Phi subscript y equal to negative 7 lambda and capital Phi subscript z equal to lambda, while capital Phi subscript y prime and capital Phi subscript z prime will reduce to fy prime and fz prime respectively, since phi contributes nothing to the prime derivatives. Plugging this into the Euler-Lagrange equations will produce a pair of coupled equations, which is negative 7 lambda minus d over dx fy prime equal to 0 and lambda minus d over dx fz prime equal to 0. Multiplying the second equation by 7 and adding it to the first will allow lambda to cancel out entirely. Integrating what remains gives a first integral relating y prime and z prime, which is y prime plus z 7z prime over set 1 plus y prime square plus z prime square equal to k. At this stage, the constraint itself is brought into relate y prime and z prime directly, since z can be written in terms of y using phi equal to 0. Differentiating that relation will give z prime equal to 7y prime minus 15, which is then substituted into the expressions above. Next, by substituting z prime equal to 7y prime minus 15 and simplifying it will lead to a quadratic equation in y prime, which is 2500 minus 50k square y prime square minus 10,500 minus 210k square y prime plus 11,025 minus 226k square equal to 0. Since the coefficients of this quadratic depend only on the constant k and not on x, any root y prime obtained from it must itself be constant. This means both y prime x and z prime x are constant. So yx and zx are linear functions of x, which is yx equal to bx plus c and zx equal to dx plus e. Applying the boundary conditions at points A and B to yx will give y1 equal to negative 1, which is b plus c equal to negative 1, and y2 equal to 1, which is 2b plus c equal to 1. By solving this pair simultaneously, it will give b equal to 2 and c equal to negative 3, so that we will get yx is equal to 2x minus 3. The same procedure is applied to zx using the boundary conditions at A and B, which is z1 equal to 0 that lead to d plus e equal to 0 and z2 equal to negative 1 that lead to 2d plus e equal to negative 1. Solving this pair will give d equal to negative 1 and e equal to 1, which is zx equal to 1 minus x. Together, yx equal to 2x minus 3 and zx equal to 1 minus x describe exactly the straight line joining A and B. Checking the multiplier will confirm it vanishes throughout lambda x equal to d over dx z prime over z 1 plus y prime square plus z prime square equal to d over dx negative 1 over z 6 equal to 0. This makes sense physically since the tangent direction along a straight line never changes. Finally, substituting y prime equal to 2 and z prime equal to negative 1 back into the arc length functional will give the minimum distance, which is j min equal to integrate from 1 to 2 of z 1 plus y prime square plus z prime square dx equal to integrate from 1 to 2 of z 1 plus 4 plus 1 dx, which equal to z 6 times 2 minus 1 that equal to z 6, which approximately equal to 2.4495. Therefore, this match the direct distance formula between A and B, confirming that the shortest path on a flat constrained surface reduces to the straight line joining the 2 points. Next, let's move to the real-life applications of Lagrangian. So, for your information, the Lagrangian method extends naturally beyond this abstract example into several real engineering contexts. For example, in robot arm path planning, J represents the path length or energy consumed by the arm's motion. Phi equal to 0 defines the reachable workspace determined by the joint angles and link lengths. And lambda x enforces that the trajectory stays exactly on this surface at every instant. Besides that, in GPS route calculation on terrain, J is the travel time or arc length functional. The constraint phi equal to 0 corresponds to the terrain elevation surface, and solving the resulting system yields a geodesic path across that terrain, which is the curved surface counterpart of the straight line obtained earlier. In addition, in structural engineering, J represents the material length or strain energy of a cable or beam, and here lambda x takes on a direct physical meaning, which it represents the internal tension holding the structure against a prescribed shell or roof geometry. In every case, the structure is identical, which extremize a functional J subject to a constraint phi equal to 0, with lambda x enforcing the constraint pointwise, is exactly as it did for the plane in the work example. Now, let's proceed to the MATLAB verification. So, to verify the analytical result numerically and graphically, MATLAB was used to plot the constraint plane together with points A and B and to compute the shortest path between them. The script confirms that both points lie exactly on the surface 15x minus 7y plus z minus 22 equal to 0, plots the straight line path obtained analytically in red, and calculates the distance directly using the norm of B minus A. The output confirms a shortest distance of 2.4495, matching the value of Z6 obtained through the Lagrangian method, and the 3D visualization shows this path lying flat against the constraint plane connecting A and B. The numerical check closes out the Lagrangian problem section, confirming that both the analytical derivation and its geometric interpretation.
Thank you, Win, for the explanation. Now, I will be taking over to discuss our next application, geodesics. To begin, what is a geodesic? As defined in our studies, the equation of geodesics are obtained to find the shortest distance on a surface between two given points. To calculate this, we rely on a length functional integrated over a curve. To evaluate this functional, we must calculate the coefficient of the first quadratic form of the first surface, known as E, F, and G. Once we have this, we will use the system of Euler's equation to find the extremal path. Let's look at the specific application problem our group solved. We need to find the geodesic between point A, 100, and point B, 012 on a cylinder x squared plus y squared equal to 1. First, we must create a parameterized equation for this surface. Using cylindrical coordinates, we let x equal to cos u, y equal to sin u, and z equal to v. Next, we find our coefficient. By taking the partial derivative of our position vector and calculating the dot products, we will find that E equal to 1, F equal to 0, and G equal to 1. Now, what happens after substituting the coefficient into our functional? Our functional simplifies to the integral of the square root of u prime square plus v prime square. More importantly, because E, F, and G are pure constant, all of the partial derivatives are exactly zero. When we apply this to the complex system of the Euler's equation, the entire first term cancels out. This leaves us with equation proving that derivative u prime and v prime must be constant, meaning the shortest path unrolled is simply a straight line. Finally, we apply our boundary condition from point A and point B to find those exact derivative. Mapping our 3D Cartesian points back to our u and v parameters, we find that point A starts at 0, 0 and point B ends at pi over 2, 2. Because the path is linear, this gives us the constant derivative u prime equal to pi over 2 and v prime equal to 2. Substituting this back into our simplified functional, we integrate from 0 to 1 to get our final solution. The exact shortest distance along the cylinder is square root of pi square over 4 plus 4, or approximately equal to 2.5431. Our group also programmed a graphical illustration using MATLAB. As you can see on the screen, this code maps the exact curve path our math just derived, proving how the straight line in the UV plane wraps around the 3D cylinder to get from A to B.
To wrap up, this project covers 3 constraint problems in the calculus of variation, and they all lead back to one idea. A Lagrange multiplier turns a constraint problem into one we already know how to solve. For the isoperimetric problem, the extremum was y equals 3x squared plus 2x plus 1 with lambda equal to 12, reinterpreted here as a beam design trade-off. For the Lagrangian problem, the shortest path on the flat plane was, as expected, a straight line, distance root 6, about 2.45. On the curved surface, that same idea gave a helical geodesic instead, about 2.54. All three were confirmed numerically in MATLAB to 4 decimal places, and the same method drives real system too: beam design, robotic, GPS, even medical imaging. One multiplier, 3 problems, one unifying idea. All from us. Thank you.